So, what is dark matter? First, dark matter is defined as matter we can't directly observe using visible or any other kind of light. However, we can tell it's there because we can see the effects of its gravity. When we add up the mass it takes to give the rotation curve we see in our galaxy, we find that dark matter has to be roughly 90% of the mass of the galaxy. In other words, we can't see what 90% of our galaxy is. Careful study of how objects in the disk and halo move tells us that dark matter is spread out throughout the galaxy's halo. Not only that, it extends farther away from the galaxy than the edge of the visible galactic disk. So the dark matter halo is the largest structure in the galaxy, as well as making up most of the mass. All of this is a little embarrassing for astronomers. After all, we've been studying our galaxy one way or another for centuries now, and after all of this time, we have to admit that we still don't know what most of it is made of. However, it's a tribute to our understanding of the physics of the universe that we can deduce as much as we can about dark matter, even though we can't see it.
We've already seen that there is dark matter in the Milky Way and most other galaxies as well. But we also see evidence for dark matter when we look at larger scales in the universe, especially clusters of galaxies. When we study the masses of galaxy clusters, we find that only 2% of the cluster mass is in the form of visible matter like stars. Dark matter makes up 50 times as much of the cluster as the obvious stars and gas. There are at least 3 different ways we can tell how much dark matter there is.
First, we can measure the velocities of the galaxies in the clusters. These galaxies are moving fast enough that if there wasn't any dark matter, the clusters would simply fly apart. So the dark matter must be present to hold the cluster together. In addition, we find hot gas between the galaxies, forming what is known as the intergalactic medium. This gas is shown in purple and blue in this image of a galaxy cluster. The intergalactic gas appears to be in hydrostatic equilibrium. Remember from the chapter on the Sun that this means the inward pull of gravity is balanced by the outward force of pressure, so the cluster gas cloud neither expands nor contracts. However, the gravity required to hold this gas in is much greater than what can come from the masses of the galaxies in the cluster.
Finally, we can see gravitational lensing in these clusters. Remember from the discussion of general relativity a few chapters back that large masses like clusters of galaxies can bend the light of other galaxies that are even further away? In this picture, we see these lensed galaxies as slightly reddish distorted streaks around the edges of the image. The amount of bending produced depends on the mass of the cluster. And once again, these masses are about 50 times the mass of the visible matter in the clusters. In this picture, we can see a map of the same cluster, now with the dark matter distribution, as mapped out by the gravitational lensing.
Even though we can't see dark matter, there are some things we can figure out about it from observing how it's distributed within and around galaxies. These properties can even help us narrow down what the dark matter could be. First, dark matter doesn't emit enough light to detect. That doesn't necessarily mean it's invisible. It could just be that the amount of light it produces is so small that we can't see it. We'll look at some of the objects that can behave like this in a couple of slides. Next, the dark matter in galaxies is distributed in the halos. It's not concentrated in the disks or bulges of galaxies, so it isn't distributed the way the stars in the galaxy are. It also seems that dark matter is, in a sense, cold, meaning that it doesn't move at close to the speed of light. We know that some things in the universe, like photons and neutrinos, do move at or close to the speed of light. If dark matter behaved this way, it wouldn't be concentrated in galaxies, but instead would be distributed much more evenly throughout the universe. Finally, we know that dark matter responds to gravity. Once again, this is because it falls into galaxies rather than being evenly spread out.
With the properties we already know, especially the fact that it doesn't emit much light, there are lots of things we know of in the universe that dark matter can't be. So let's see what we can rule out about dark matter. It clearly isn't made of stars. If most of the mass of the galaxy was in the form of stars, even low-mass M stars, we would be seeing the visible or infrared light they produce. We also know it can't be gas. Depending on the temperature and composition of the gas, it will emit light in the radio, infrared, visible, and at high temperatures, even the X-ray parts of the spectrum. So we'd see it if there was that much gas in the universe. In fact, in almost all galaxies, the amount of gas we can observe is far less than the amount of stars. Dark matter also can't be dust. Dust grains emit infrared light, and if there is a lot of dust, then it blocks visible light, so we'd notice large quantities of dust in the galaxy. Also, having that much dust would mean that there must be many more metals than hydrogen in the universe, which makes it hard to understand how stars could form mainly out of hydrogen. So if those are the things that dark matter can't be, let's have a look at the two main types of objects that have been suggested for what it might be.
One candidate for dark matter is something called MACHOS. MACHOS is short for massive, compact halo objects. This is really a cute way of describing large objects that don't generate much light. There are several types of things that could be called MACHOS. These include free-floating planets that aren't orbiting any star. Brown dwarfs. Remember that these are stars that are too small to start nuclear fusion. And stellar corpses, like neutron stars and black holes. All of these have the property that they pack a lot of mass into a very faint package. So if there are enough of them around, they could account for more mass than the stars we see. Starting in the 1990s, astronomers began looking for MACHOS in a systematic way. The technique they used was called gravitational microlensing. We've seen that large masses can bend light. If a faint, massive object gets exactly between us and a more distant star, the distant star will get brighter as the MACHO's gravity acts as a lens, magnifying the star's light. While this is a very rare event when observing any one star, if you look at hundreds of thousands of stars on a regular basis, the odds that one of them will be lensed can be quite good. The graph at the top shows a lensing event. The vertical axis shows the brightness of the star, and the horizontal axis shows time. You can see that partway through the set of observations, the star suddenly gets a lot brighter, and then gets dim again. That's the sign of a MACHO passing in between us and the star. By counting up the number of microlensing events like this, we can get an estimate of how many MACHOs there are in the galaxy. Unfortunately, there aren't nearly enough to account for all or even a large part of the dark matter we observe. So, we need another candidate.
The other major candidate type of dark matter is called WIMPS. The term WIMPS means weakly interacting massive particles. No, the contrast of the two names isn't an accident. WIMPs were named first, and the term MACHOS was developed in response. What WIMPs really means is a new type of subatomic particles, not protons, neutrons, electrons, or any of the other particles that we haven't talked about. WIMPs are similar to neutrinos, those extremely low-mass particles produced in nuclear reactions that pass through almost any matter. However, unlike neutrinos, WIMPs have much more mass, so they can produce more gravity. The weakly interacting part of the name means that WIMPs don't react with any kind of electric or magnetic field. At the atomic level, ordinary matter reflects and emits light because it reacts to electric fields. Since WIMPs don't have to react to electric fields, light simply passes by them, making them impossible to find using light. In fact, WIMPs can pass right through ordinary matter for the same reason. They don't interact electromagnetically, so there's almost no way for ordinary atoms to stop them. WIMPs and neutrinos still interact with other matter using a different force known as the weak nuclear force. This makes it possible to detect or create them, though in the case of WIMPs, they are right on the limit of what can be produced in current particle accelerators. The first hints may have been found, but it will take time to decide if this really is the source of dark matter. However, at the moment, WIMPs are the leading candidates for the bulk of the dark matter in our universe. It may seem strange that scientists would be willing to predict the properties of a particle they have never directly observed, but in this there is already plenty of precedent. Neutrinos were first predicted based on models and nuclear reactions, and at first they seemed equally unobservable. However, many years after they were predicted, scientists were able to observe them and determine that they really did play the role predicted for them in these reactions. This is a classic example of making and testing predictions, as we discussed near the beginning of the course.
Before we finish with dark matter, it's worth mentioning that there is one class of explanations for galactic motion that does not involve dark matter at all. Remember that the reason we assume the existence of dark matter comes from observations suggesting that the gravitational force on the galactic scale is too strong for the amount of matter observed. However, what if the problem isn't with the amount of matter, but instead with our understanding of the gravitational force? Some scientists have argued that there may be additional terms in the equations that describe the gravitational force, and that these only become noticeable on very large distance scales, like thousands of light years or more. If this is true, then it may simply be that the matter we see is producing all of the force without help from any unseen matter. However, folks working on this approach have had trouble making it fit with general relativity, as well as some of the observations of gravitational lensing. In particular, many of the gravitational lensing observations suggest that the gravitational force doesn't always follow the same pattern as the visible matter. This couldn't be caused by a change in the gravitational force law. As a result, most astronomers consider dark matter to be the more likely explanation. So, to summarize what we know about dark matter, about 90% of all the matter in the universe is made up of dark matter. We can detect its presence through the effects of its gravity, though it emits and absorbs too little light to be observed. Within galaxies, dark matter is mostly in the halos, though there is also a lot between the galaxies in galaxy clusters. While there are several types of ordinary matter that could produce the effects of dark matter, observations have ruled out most of these, so that the most likely candidate for dark matter would be a new class of subatomic particles called weakly interacting massive particles, or WIMPs.